And this this webinar is under the working group 5, which is on materials and chemistry. And yeah, if you have any questions, please, you can write it in the chat, or you can also raise your hand. I can give you the ability to use your mic. And yeah, I think it's all yours.
Okay. It's my turn to present my work, right?
Yep.
Okay, sure. So let me share my screen. Okay. Okay. Is it perfect?
Yes. Looks good.
Okay, sure. Thank you. Thank you, everyone. And thanks to AI Alliance. And today I will present my work, MatExpert, Decomposing Materials Discovery by Mimicking Human Experts. This work was just accepted by ICAR 2025, and we collaborate with Interlabs for this week for this work. So first, I will introduce our task. We aim to AI-driven materials generation, and our goal is to generate stable crystal structures, is represented by CRF, and that match usual defined property constraints. For example, the band gap, the stabilities, space group, and compositions, and so on. And the input to the framework is very simple. It's like it's actually based on language. For example, I'm looking to design a new material with the following properties. For example, the formation energy, the band gap, the energy above the hull, elements, and space group number, something. And the outputs of our framework is the CRFs, which represents the most likely material that satisfy the input usually defined property constraints. And CIF is very popular to represent the structure of a material. So this is the output of our framework. So here is why materials discovery needs help. In traditional scenarios, if we want to design a new material, we have to utilize the human experts may utilize some tool like DFT, and the traditional methods are mostly expensive and slow. For example, DFT simulations for even one material would take hours to days of computation. So a lot of AI approaches emerged to figure it out. For example, the most recent work with large language models called Crystal large language model, which directly outputs the structure from text, but it's a pretty straightforward approach. So there's no chance to revise or refine the structure inside the framework. And second work is LMCH and LMAC, which is very weak grounding. It's actually with the transformer-based architecture, but only with weak grounding between properties and structure. And the last is CSP, which is a diffusion-based model, and it is great for unconditional generation, but it is not language-based, so it's very hard to condition on user-defined properties. So now we introduce our framework. The key idea is that MatExpert reframes this task as a human-like design process. So we enable interpretable step-by-step generation. So briefly, our MatExpert framework can be decomposed into three stages. The first stage is retrieval. So first, uh, it's somehow like the human pipeline. The first, we want to, given a task, we want to first find a reference material, and we uh, modify the reference material to get some novel features, and then finalize the structure. So first the stage is the retrieval. We first retrieve the most similar, the most likely material in our large-scale database. For example, here the input is space number is 5, a band gap is 1.1 or something, and then we retrieve the most similar material from our database, which is like this formula. And then the second stage is called transition, which aim to modify towards the targets. So it might the framework might give some hints like replace now with Lee and change the space group number or something, and then we give a new structure or new formula like this. And then the last stage is the generation. And it's like a calibration, like we finalize the structure based on the all of the previous thinking. So our framework is actually property-driven generation, conditional generation, and we also support iterative refinement, and reduces the hallucinations. So here is the overview diagram of our framework. It's more like a multi-turn conversation, but not all of them based on large language models. For example, first we input our constraints. Below is a description of bulk material, the formation energy, the band gap, blah, blah, blah. And the first stage, in first stage retrieval, we first, we pre-trained a contrastive learning framework to embed, to align the structure and properties in same space. So we have a retrieval stage, more like a rack, and so we can retrieve the most similar material in our large-scale database. And here we retrieve one. So this stage is not large language model based. It's actually vectorized similarity computation based. And after that, we retrieve reference material from the database, and we got all of the descriptions and the structure and properties of this reference material. Then we will ask the large language model, how should I modify this reference material to develop a new material with the desired properties? And so the second stage in the transition stage, our framework, the large language model will output some thinkings like how to transit from this reference material to a new material. And after that, the last stage is the generation. We based on all of the historical terms of conversation, the large language model will generate the final ALX representation, which includes the coordinates of atoms, the latest parameters, and something like this, the basic information to have to build a structure of material. So that's the whole pipeline whole diagram. So let's step by step in deep. So here, this is the first stage, retrieval stage. To align the space of structure and the properties into the same space, we trained dual T5 encoders for property and the structural descriptions. So the property description and the structural description are both described with language, not with some other formats. And for properties, it just pretty similar to our inputs. Like it includes the composition, band gap formation, and something like this. We sample some, and for the structure description, it is actually auto-generated using a tool named RoboCrystal Grapher, and it can automatically translate CIFs into human-readable text. So we can utilize two language-based encoders to embed the properties and the structure into the same space. So after that, here's the second stage, which called the transition stage, which also with the chain of thought reasoning. In this stage, we transform the retrieved material into a new one that satisfies the desired properties. We do not directly utilize general purpose large language models in our framework. We actually fine-tune a large language model with Llama 2 and Llama 3. And but we encountered a problem that we actually do not have the ground truth pathway, like ground truth thinking pathway. So to build the intermediate turns of our conversation, we utilize GPT-4 to bootstrap the ground truth transition pathways generation. The details are that we give the GPT-4 with the ground truth material and the retrieved material, and then so the GPT-4 can generate the pathway from retrieved material to the ground truth material with some prompts. And then we utilize the response as the ground truth chain of thought reasoning for our the fine tuning of Llama. So that's how we build the data sets to fine tune our Llama. And from the left to right for our framework, the first stage is the retrieval. We first given the desired properties, we first retrieve the material from our database. And then we have the GPT-4 bootstrap that we have the ground truth material, which exactly satisfied the desired properties. And we have the retrieved material from the material database. Then we can generate the ground truth pathway. Then we can use the ground truth pathway to fine tune our Llama. This is the first turn of the conversation. And for the second turn of fine tuning is actually the third stage, the generation. We already have the generated material. We already have the ground truth material, so we just use the ground truth material to fine tune to fine tune the generated material for this second turn conversation. And the last step is the conversion and relaxation. It's like to make the perfect structure, the more perfect structure. Here is an example how we bootstrap GPT-4. So we utilize the following prompt, given the ground truth source and target, which is the retrieved material and the ground truth material. And with this prompt, we can generate step-by-step transition reasoning to fine-tune the Llama. and it is actually stepwise scientific logic, and so it's not a black box guess. That's our, I think that's the key of why key of the reasons why we uh, outperform previous methods. And here is the generation stage.
One one
It,
question on the previous slide.
yeah,
So you used GPT-4 to get the ground truth description of how
pathway.
to move from source to target,
Yeah,
right?
exactly. Yeah,
I would assume that GPT-4 doesn't have all the knowledge to give you the correct ground truth all the time. So do you know like what's the percentage maybe of like accuracy
yeah,
in that sense?
yeah. We don't actually we don't we didn't evaluate the accuracy or something. Just I think with the existing resources, it's the best way to have these pathways. And I don't think we the pathways, the data sets should be like exactly 100% accurate to fine tune the llama, right? We actually we allow some raw information here, just just as a fine tuning. So I think some noises are allowed here. Yeah,
Okay, okay, thanks.
yeah, yeah. So here is the generation stage. Generation stage, we utilize the ALX as the output, the response to the fine-tuned large language model. That because it is more concise and simple and due to the limitation of contextual size of Llama 2 and Llama 3. We cannot have such long such long response like the CF representation. So here we utilize ALRX, which already I think it already includes the necessary information of the structure, like the lattice, the lattice parameters and the coordinates. And we enrich the representation, utilize the tool PyMetaGen, and also we relax the structure with some like M3G net or DFT to have the final CF representation. So after that, the final materials will, I think, will property aligned. And, that's the first step. That's the last step. And here I want to introduce our dataset construction. To fine tune the large language model, we should have a large scale dataset. So our datasets include two parts. The first part is Nomad, which is collected by ourselves, and the second part is Material Project, which is a very publicly well-known publicly used datasets. So for Nomad, we collect the materials from Nomad libraries, and it's a pretty large scale datasets. We include nearly 2.9 million crystal structures. And we utilize some filtering criteria, like we exclude inert elements, and we keep only materials simulated with the VASP, and we discard structures with greater than 30 atoms. So, and for material projects, we just utilize the MP20 subset from the prior work, which is the same as the prior work. It includes nearly around 45,000 stable materials. Yeah, that's it for our approach and dataset part. And here is the comparison results for unconditional generation, which is like no input desired properties. And even with this scenarios. We outperforms all of the baselines, the Crystal AM and CDVAE and AMSCH, and all of these baselines. And actually, especially we are pretty strong on distribution, because we have a reference material, but others just design a new material from scratch. So we keep the distribution between the generated one and the one already in our database. So it's a key advantage. And the second comparison results is for conditional generation. And we have here we have the only baseline we can compare is the crystal large language model, which also support flexible inputs. So here is the results. Actually, we also outperform it with a large gap, and also in our analysis of conditional satisfaction, we have higher ratios than the crystal large language model. Here is four case of our framework, just from left to right side. So it's the same as before. The first term is the input is the user defined desired properties, and we retrieval, and we describe the retrieved reference material with language, which includes the structure, the properties, and all of this information of the reference material. And then we the fine-tuned llama will output the transition pathway, how to transit from the reference material to a new material that satisfied the desired properties. And then last stage is the generation. We have the LRX representation, and after that, LRX representation will be converted by PyMetagen library to have the CIF representation, and then we relax the CIF representation by M3GNet. So then we have a relaxed and stable structure for this material. So that's the whole pipeline of our framework. So now we can have a conclusion here. The MatExpert, it actually bridges the large language models and scientific reasoning, and the approach we believe it paved the way for interpretable, controllable material design using foundation models. And we in the future we will explore more more directions. So for example, the first is the closed loop material discovery. We will investigate how to integrate synthesis and test and refinement in our generation, and we may use active learning and or reinforcement learning to propose or post-process the structures to further refine and calibrate the structures. And beyond the materials science, we believe our work can be generalized to other fields like drug discovery, protein engineering, molecular design, or something. And I think it's a standard pipeline that from learning from mimicking from the human experts experience, and with the three stages: reference, modification, and creation. So yeah, that's it for my presentation, and thank you for listening. Any questions here?
Thank you so much. Yeah, if you have any questions, you can write in the chats.
Yeah.
I have one question, and actually you touched it a bit on the last slide,
Yeah.
which is like right now you're using, yeah, like ChatGPT to create the description, and then you fine tune Llama. I think you use LoRa to fine tune it, right?
Yeah, exactly. Yeah, with LoRa. Yeah.
So yeah, so and nowadays, they're for to activate reasoning, people are using like RL,
Yeah.
um, right?
Yeah.
So do you think there's gonna be a bigger gain by using RL on Llama rather than this fine tuning?
Yeah, with RL, it's more flexible. With the, it's like, it's there are totally two directions. With LoRa, it's more like a supervised learning, right? We have a key answer, and we utilize the key answer to supervise the learning of the training of the model. And with the enforcement learning, we can have more flexible. We can have the reward, and maybe we can have we can include human feedback, and it's more flexible and include more information. So it's basically, I think it's a better way, but it may take more resource, computational resource to for our reinforcement learning, the loop of reinforcement learning. So yeah, that's actually our future plan, some future plans. So it deserves to investigate. Yeah, it's a
Yeah.
very good suggestion. Yeah,
Okay, cool.
yeah.
Um, so I don't know if there are any questions, or I think
Mm-hmm.
it's super clear. Um, yeah, maybe we can wait for a bit.
Yeah, I think.
Oh, and there is a question. One sec. I need to give you.
Yeah, let me quit and check the chat box. Chat box here. Just raise a hand, right?
Yeah, I just gave the person the ability to talk.
Hi. How subtle can you test for differences between materials? I mean, I'm not a crystal person. I'm a surface person.
Yeah.
For example, for liquid-like surfaces, it can make a huge difference the length of the chains attached to the surface. Um, because you're using two different models, how subtle material differences can it go? I think you had a table showing one of your tables. Yeah, I think maybe that one. Um,
Yeah. So
I mean, do you see only like trends, larger trends, or can you also be applied to areas where there's very subtle differences between materials, which end up in very enhanced difference in properties?
I'm not quite. Sorry, I'm not quite understand your question, but it did related to like how we the evaluation of our framework.
Yeah, for example, how you evaluate it and how you can vary on like the ground truths you have,
Ah,
how fine the variety is you have on the ground
okay,
truths.
okay. For the metrics, I can introduce some about the metrics. The first is validate check. So we have two validators. First is structure, and second is composition. That if it is like the same, it is if it is the structure like we can recognize, and if the composition mm, is correct, and with the chemistry or with the material science knowledge, and there are already some tools to check the validity. And second is the coverage and the distribution. I think they're both for like to describe the generated materials with the materials already in the database that uh, that if it is a line, the distance is aligned with the database, something like that. And also, this is for this is for conditional generation. So we also have a metrics for condition satisfaction, that how much material satisfied the properties, desired properties input to the framework. And for unconditional generation, we also have meta stable and stable. These two matrices are for stabilities. So that we utilize the M2GNet and DFT with also tools to validate the stabilities. Yeah, that's it for. Yeah, so basically, we use tools. I think for all of these metrics, we have tools to check, because we already have the CF the output of our framework is CF representation is pretty common in material science. So a lot of tools to check the CF files, CF representation, if it is valid, if it is stable, something like that. And we can very simply extract the features, the properties of the generated material using CF files. So it's convenient here. Yeah.
And how many, thanks a lot. And so how much quicker would you be than like just somebody by hand drawing such a material, which given that of course that would not maybe have the optimal attributes you search for, but like if you had like a hand drawing material as like an roughly optimized material as a like how much more of an enhancement are you in time saved?
Yeah, the first is we can our generation. So yeah, I understand your question. So first, the output of the framework is actually the ALX representation, and we can utilize tool like PyMetagen and M2GNet to relax and convert the ALX, the output of the model, to the CRF representation. Actually, this step already like filter out the wrong structures, some wrong structures. So here we already have a filter, and with the relaxation, like M3GNet, we can already know the stable, whether it is stable here roughly. It's not a exact correct approach, but it's an estimation approach, but it's very quick. That just take seconds for this step conversion and relaxation. So if you want an exact correct exact correct information of the generated material with the DFT, it takes very long, like several hours for a material, but it's not less necessary. I think only with the PyMetagen, the M2GNet, and some other quicker estimation-based approaches, enough to know if whether the generated one is useful or valuable. Yeah.
Thank you.
Yeah. Thank you. Thank you very much.
One comment on the previous question. I think they were asking if the length of the chain can make a difference, and I think for your case with crystals, you have just one repeat unit, right? Because it's a bulky material.
Yeah, exactly. Here, so you mean can we have more more thoughts in our chain of thought, right?
No, I think it actually means the chain in the material itself. So, for example, or maybe not, the length of the chain.
I mean, like very, very subtle differences in the basic structure. I mean, this was a example from surface sciences where when you have like polymers stick to a surface,
Mhm.
um, it can, but it doesn't have to. In certain cases, it makes huge differences. And I know for certain crystals, for certain types of crystals, you have a similar situation that subtle differences in the cell can make a huge difference, but not for all crystals. So I wonder if, because these are the hard problems in a way, this is not, I mean, like also when you think about like a subtle difference makes a huge difference, how to synthesize it then. So I wonder if you looked into that particularity, um, like of materials which subtle differences make a huge difference, yeah, in properties.
Uh, yeah, I understand. So,
I
let me think how to, yeah.
I have
So
I have one,
mhm,
I have one comment on that because I work on polymers,
mhm,
and you still, at least for what I do, something like this, I still represent the polymer as a monomer only, like the repeat unit, and do the same, use this framework, for example, because
mhm.
you only need like the repeat unit. And then how you consider the, yeah, for example, the chain length would change the
Uh,
property. I guess that goes back to like MD simulation and DFT when you like verify it.
okay, so you mean there's maybe some something cannot include it in the unit cell. For example, there are some other properties of chain inside the structure, crystal structure, right?
Yeah, exactly. I think that's the question.
Yeah,
Pretty much.
yeah. Actually, to be honest, I'm not a material scientist, and I just major in computer science. And I understand your question, but actually I have no knowledge of material side to explain that. But for your question, I think maybe in the future we can mm, we can include the more to response in our last stage, and the chain, some properties of chain, and maybe it works. And this work was done in the last year, so we can only use the Llama 3, and Llama 3 has a very short contextual size. But now we have more choices, like Gemma, Q1 or something. And with the latest large language models, we can include more terms of conversation and more information in our input, also the output. So yeah, in the future, I think with the new models, you design of the conversation, you prompt, maybe we can figure out. Yeah, yeah, that's it. Hope can understand your question. But honestly, I'm not a material scientist, so sorry about that. But our team, the second author is specialized in material science, so we work together for this work.
Are there any more questions? If not, we can wrap up. Thank you so much for presenting.
Yeah,
Um,
thank you.
yeah, it's really interesting work.
Yeah,
We'll be uploading the recording soon to YouTube. I share the link to the playlist in the chat. And yeah,
mhm.
thank you again. Have a good day, everyone.
Thank you, Luis. Thank you, everyone. Have a good day. Bye bye.